Okay, so here are some thoughts on the Foucault pendulum thing and trying to do it in kind of a lightweight sort of way. So I think you probably need to start with talking about the cross product. All you probably need to say about the cross product is the cross product of A and B is perpendicular to A and B, and that so there are two directions perpendicular to A and B. It's the one so that A cross B is a right-handed set, and its magnitude, crucially, is mod A, mod B, sine theta, theta the angle between them. Okay, so once you've got that notation set up, you can have a think about, suppose you've got the Earth here spinning with angular velocity omega, so that means it's around the axis labelled omega, and you've got some position vector r in blue. I'm interested in the velocity of this point here from the perspective of somebody fixed, somebody not on the rotating frame. So that velocity comes in two bits. One bit is the bit due to the rotation of the Earth, and that bit will be, it'll go into the screen as we currently see it, and its magnitude will be the angular velocity omega times the radius of the circle it's moving round. So it's kind of moving round a circle like that. Oh wow, that's bad. So that's r sine theta. So its direction is into the screen. That's perpendicular to omega and r, such that omega, r, and this bit of velocity are a right-handed set, and its magnitude is omega r sine theta. So brilliant. So that contribution, the contribution from the rotation, is exactly omega cross r, hence the useful cross product notation. And then there's also a contribution from r dot. That's how an observer on the surface of the planet would see r moving. Okay, so this is velocity from the fixed frame, and now the real trick is to find acceleration in the fixed frame. To do that, I need to do d by dt of the thing I just found, the absolute velocity, that's r dot plus omega cross r. But I have a rule for how to do that. How do I do d by dt of something? Well, I dot it in a sort of rotating frame, and then I add on this extra term, which is omega cross the thing I was trying to differentiate. So I get r double dot plus omega, we're going to say, is fixed, so omega cross r dotted gives me omega cross r dot, plus omega cross the same old stuff, r dot plus omega cross r. Okay, so this is exciting. Now what we'll do is we'll assume that we have a particle of unit mass, so m is 1, and we'll apply Newton 2. So Newton 2 works in the non-rotating frame. So I can replace this capital A with the force acting on the particle, the true forces, non-fictitious forces. So I've got F equals r double dot, that's the acceleration as measured in the rotating frame, and then I'm going to expand out the brackets and rearrange them a little bit. I'll put this term first, omega cross r, and then I've got two lots of omega cross r dot. Okay, and then finally I'll rearrange to make r double dot the subject, so I get the acceleration as measured on the rotating frame is equal to the force per unit mass as measured in the fixed frame, and these extra terms are the fictitious or inertial forces. So there's one missing because I assumed omega was constant. There's like an omega dot one. Okay, so at this point you need to like pause and think long and hard about what these things mean. So in particular, we've got to understand the cross product notation about the direction these forces point in. So this one here is the centrifugal force, and I'm genuinely going to call it centrifugal because it's on that side of the equation. It's sort of from the perspective of someone on the rotating frame, this is genuinely a force fleeing the center of rotation. Its direction, well, it's perpendicular to omega, definitely, because it's omega cross something or other. And the other thing it's perpendicular to is omega cross r. Okay, so on the picture up here, the things perpendicular to omega sort of form horizontal planes, I guess, if omega is pointing straight up. So it has to be in one of those planes, and it's also got to be perpendicular to omega cross r. Now omega cross r points into the screen currently, so that means it's in the horizontal plane and it's perpendicular to something going into the screen. So that means it goes like that. Okay, so this is the centrifugal force in red. Okay, notice it doesn't directly counter the weight or anything like that. It has a component that contributes to reducing effective gravity, and it has a component which kind of forces particles to move towards the equator. Right? So this is why the Earth is an oblate spheroid, because stuff gets squished out to the equator by the centripetal line. Okay, and then what we're really interested in is trying to understand this term, this minus omega cross r dot. This is the Coriolis force in like beautiful purple, and we want to understand that thing's effect on a pendulum. So what I thought would be handy would be, first let's try and understand how these equations work. Whoa, that's a terrible circle. In context where we already qualitatively understand what Foucault's pendulum is doing. So let's have Foucault's pendulum set up at the equator. If that's the case, then we kind of already understand that the pendulum will precess round from the perspective of a rotating observer at the rate of 1 revolution per day. What is this equation telling us? Okay, so r dot is going backwards and forwards like that. And it's got, notice by the way that there's no centrifugal force at that point, I think. But anyway, what is the Coriolis force doing? Well, it's perpendicular to omega, and it's perpendicular to r dot in such a way that omega r dot and the omega are right-handed. So here, in this case, the centrifugal force, sorry, the Coriolis force, points directly into the screen, and that's the force which kind of makes the thing rotate round at a rate of 1 per day. Fantastic. So that makes sense at the North Pole. Does it make sense at the equator? Okay, well, let's try another picture. Let's get rid of R over there. Okay, let's have, at the equator, there are a couple of things we could do. Let's set the thing, the pendulum oscillating so that it's oscillating north-south to start with. What's happening here? Well, here, omega cross r dot is 0, because the angle between these two vectors is 0. So there's no Coriolis force here, so no rotation. Easy to understand. Okay. Interestingly, if you're at the equator and you set your pendulum going, let's say, into the board, I can't remember if that's probably out of the board, isn't it? Into the board I think is like a cross. So if you've got r dot going into the board, then you have got a Coriolis force, and it's perpendicular to omega, which points up, and r dot, which goes into the board. So the Coriolis force here points, see if I can get this right, I think the Coriolis force here points into, or sorry, the cross product points into the surface of the sphere, and so minus 2 times that cross product, the Coriolis force in purple, in this case points out. So it's not that there's no Coriolis force at the equator in this case, it's that the Coriolis force acts perpendicular to the direction of rotation, acts directly out of the surface of the sphere, so it doesn't cause any rotation. Doesn't cause any precession. Let's suppose that you are at the equator and you set the thing moving at some direction that's not north-south and also not east-west. You just need to view that as a linear combination of a north-south component and an east-west component. Neither the north-south component nor the east-west component cause precession of any kind. So at the equator, Foucault's pendulum doesn't precess. Okay, so this fits with what we expected. And now the interesting bit is what happens if we're at some particular latitude. So, okay, let's, I don't know, orange. Okay, so we'll go to some latitude. Theta. Sorry, different theta to the one above. You'll live with it. Okay, so let's first of all see what happens to Foucault's pendulum if it's set off going north-south to start with. So r dot goes to the north. Yeah, sure, why not? So the cross product. Okay, so we have to like zoom. Do you mind if I draw another second copy of the omega vector just there? The picture's too small, but never mind. Geometry shows that this little thing is a theta as well. Okay, so the cross product first of all is pointing omega r. I think the cross product to make omega r dot and their cross product of right-handed set points out of the screen, so the Coriolis force, which is minus 2 times the cross product, is going to point into the screen, I think. So that's like that again. Okay, so it points into the screen. It's perpendicular to r dot, and so that's the force which is going to cause the thing to rotate. But how big is it? Well, its magnitude is, at any particular moment, mod r dot mod omega times sine of the angle between them. That's sine of the latitude. So if you compare this to a Foucault pendulum spinning with the same r dot at the North Pole, the effect of the precession, or the force causing the precession, is initially sine theta, is less by a factor of sine theta. Okay, and because the force, all the force is doing is changing the direction, this force which is constantly less leads to a lower rate of change of direction, so the precession will be slower by a rate of sine theta. That's if the Foucault pendulum is initially set spinning north-south. Right, let's try the last one. If it's initially set going into the screen, so r dot goes that way. Now, stressful. Where does the Coriolis force go? First, let's try and figure out where the cross product goes. So the cross product is perpendicular to omega and r dots, right-handed. Omega. So I think the cross product points. Sorry, omega. Yeah, the cross product points in towards the axis of rotation. The Coriolis force minus 2 times the cross product points out like that. Okay, so that's weird. No sine theta anywhere here, and what's happening? Well, what's happening is that this Coriolis force then has got some component which is which is reducing effective gravity, and it has another component which is causing r dot to rotate. So I think it's got a sort of downwards component and an outwards component. And the downwards component, let's just do a bit of geometry, theta, theta. I feel like there should be a theta here. Let me do that in orange. Okay, so again, do some geometry. There's a theta here. So the component of the Coriolis force which acts in the plane of the surface of the Earth and is causing r dot to rotate, because it's perpendicular to r dot, is still mod omega mod r dot sine theta. So the sine theta comes in for a different reason here, but still less than it would be at the pole by a factor of sine of the latitude angle. So and now you're done. If you have it spinning at any angle, you view that as a linear combination of some movement in the north-south direction, some in the east-west direction. Both are less than they would be at the equator by a factor of sine theta, so there's your sine theta, and you're done.